My name is Carlos Femmer. I'm the Director of Data Acquisition with HDR Engineering.
Hi, I'm Cameron Schaefer. I'm our Transportation, Data Acquisition, and Reality Mesh Director.
The scope of the project was to create a digital twin or reality mesh to complement 3D model where we're going to leverage AI.
So we took the orthomosaic imagery that we had from the reality mesh, popped it into Neurala Brain Builder, which is through a web portal. How many of those different assets there are within that 45 square mile. So it gave us a count, it gave us an understanding.
Well, you could probably guess if you do no remediation that the predictive analytics on it is going to be 3 centimeter growth if nothing changes.
And at the end of the day, we're just looking to continue to build the group of users that work with this type of technology, right? Get them more familiar, get them more excited, and make this more part of the day-to-day work that we all do.
Today's presentation is going to be on leveraging reality captured data to solve tomorrow's infrastructure challenges. My name is Carlos Femmer. I'm the Director of Data Acquisition with HDR Engineering. And
hi, I'm Cameron Schaefer. I'm our Transportation, Data Acquisition, and Reality Mesh Director.
So just we have one slide on HDR Engineering. It's been around for 100 years. Established in 1917, 40 plus countries, roughly about 10,000 employees, 200 plus offices worldwide. Within the data acquisition practice, we have about 125 data acquisition professionals. 2020, we completed about 568 projects. And from a core offering, we have artificial intelligence, survey, drones, LiDAR, geophysics. So when we talk about reality capture and whatnot, the ability to bring in a lot of these sensors, we're going to look at a few project examples. It's pretty beneficial. The first project example that we're going to talk about is Diablo Dam. This is for Seattle City Light up in Cascade National Park. So this particular project, the scope of the project was to create a digital twin or reality mesh of the dam. It's to complement, it's a 3D model where we're going to leverage AI and produce a digital twin of it where you can do inspections from it, have a baseline from a survey. Our role was to perform drone inspection used to create centimeter grade accuracy and then use AI for data analysis. And then benefits to the client or final deliverables were digital twin, crack detection, prediction, and enhanced asset management tools. So if we look at the execution for the project, it's broken down typically into 4 phases. The first phase is inspection or the data capture. We use drones. We set survey control, or first we got the survey control from the client. We went set up on their survey control, set out ground control points from there, and then did a particular capture and technique for that specific dam because each asset requires a different capture technique to get it the right way. The second part was data collection. We ended up with 82 million points, 2 centimeter accuracy of what's stated. It's actually tighter than that. And then ground control. Data processing, we created the digital twin with Bentley's context capture, which is an amazing software piece. And then lastly, we developed some AI to do some crack detection, and it helps out with future repair, maintenance as well. So the whole goal was to create a living, breathing model, and the first part is high-resolution photography. In this particular project, we did, the next project we'll talk about is where we brought LiDAR in, but in this particular one, we didn't have it. So you have high-resolution photography that's overlapped both side and front to produce the reality mesh and digital twin. The second is the ground control, survey data, and LiDAR. The point cloud, and then in the future, where you can throw in other sensors is where things are going. If you have a baseline and you're adding that same capture year over year, or at whatever cadence is appropriate, some assets might be 2 years, some assets might be every 5 years. Then you add in other connected sensors, that's where you bring a lot of things together. So the focused and future is on asset management, extending the range and accuracy at a lower cost. So what we're doing is, to state up front, we did the rope inspection, but this is a complement. This isn't a replacement for what a rope inspector would do. You can't bang on things with the drone, but what you can do is get a good complement as a tool to a rope inspector where appropriate. If it's just a visual inspection, then it's the right tool for sure. Machine learning and AI, we're going to talk about that shortly too, and the effectiveness increases exponentially with time. And we'll talk about that in a second as well. But if a good example is, year 1 you capture it, you see a crack. Year 3 you capture it, and that crack extended by 5 centimeters. And then year 6 you capture it, and it's 9.2. Well, you can probably guess if you do no remediation that the predictive analytics on it is going to be somewhere at 3 centimeter growth if nothing changes. But it starts with so here's an example where we took the dam. This particular project, like I mentioned, was in Cascade National Park, required a special waiver and permission from the Park Service. It's challenges here. If you look on the right, we requested that all of the spillways be shut off. They weren't able to for that time of year when we're on site. So we had to get creative and say, if you look at it, if you're doing photography and with a drone, that mist is going to give you this artifact in the cloud. So we were able to work with them to say, can you guys, you can't shut it down, but can you just close it to like 2 inches? And that eliminated a lot of the mist. And beyond that, we had to adhere to launching and taking off from property. We set the survey control. But I think the end result was phenomenal when you look at the results. I think we did an interview with CNET that published this as well, and we had some good feedback from that along the way. So we'll talk about AI, and we keep it simple. It's 3 buckets. AI is when a computer can do something that requires intelligence by a human. Machine learning is a subset of AI that uses algorithms to train machines to perform tasks intelligently. And then deep learning is a subset of machine learning where neural networks learn from vast amounts of data. So if you hear these 3 terms, they're typically talking about one, but one fits inside of the other that fits inside of the other as well. Kind of here, how does it work? You throw in, at a high level, we took thousands of pictures and you train the data to say, what is a crack? So you throw in the raw data, and then if you look at the top right, there's your output, and that just iterates over images. So 2 ways to do it: let the machine do it, or let somebody take the image and try to find those themselves. Kind of how it works as a workflow, so what's cool about it is when you take the drone and you put in your parameters, it's going to capture everything on your SD card, all the images you collected. You take that, do a little drag and drop action into a folder and say iterate over all these folders, and then you train the data, you refine it in time, and then just kind of our secret sauce, we feel, is we're not inspectors. So having the inspectors do the training of it is what's important, and we'll talk about that here shortly too. So there's a video that plays here, but on this video, what happens is the inspector would go in, they would delineate what the crack is, what's not a crack, and then that kind of that teaches the machine, this is a crack, right? And then what happens is, here's a result. We try to get creative at the beginning and say, well, instead of creating our own algorithm, why not find it public domain and off the internet? So we did that. We found a public data set for roads, and we applied it to this, and what you can tell is it did pretty good. Coming back to the left, you'll see cracks and you see spalls. It found cracks, but it found cracks in trees, and it found none of the spalls. And then whenever you dial it in and train it and run it again, it finds it. So here's a close-up of it. This was kind of the public domain. The cracks did great, decent. But whenever we trained the data set and ran it, this is what it found, and that's kind of what the end result is. You want it to assist you. So imagine doing this for over thousands of images. The second project we're going to talk about is San Diego Murray Dam. This was a unique project. Just talking about, this is a reality capture. We talked briefly about the techniques. So here you want to have your nadir flights. Everything's kind of programmed where you want to be the right distance off of the asset. So in this particular case, this particular flight was 4mm accuracy. We used 3 different drone types for the capture, or actually 4 in total. But we had an RTK drone, the Matrice 300 on the top, using the P1 camera. We said, okay, you have to fly at this altitude, 104.8 feet. Front overlap 80%, 60%, and then we're going to fly at 9 miles an hour, and it's going to be a 6-minute flight. So go. And then it captures and it comes back. Next, you want to have your obliques, and the certain technique is you want to have your conditional yaw. So I want to capture 45 this way, 45 this way on both sides of it. That captures your top. Coming back to here, now I want my facades. So I'm going to have a 30 degree, and you're going to capture that. And again, dependent on how close you want to be, you want to be the right distance to where if you're saying I want a 4-centimeter accuracy model, then your top, obliques, facades all need to be the same resolution. And then on here, we actually captured LiDAR as well. This was a complex project. Numerous scans. I heard presentations before where you talk about shadows. Same scenario here. You want to make sure you paint it and you get all the data that you're looking for. So after we painted it with numerous scans, we ended up with over 1 billion points. We had RTK, Trimble R12 out there. We used an SX12, and then we used the X7 inside the bay. So we used 3 different LiDAR systems to get the data that we were looking for. So a little over 1 billion points. Yeah, so this video is playing. So here's what's here on the left. You have your external bays, your facades, and then every one of those facades there has an internal bay. So as big as it is outside, it's just as big on the inside. And then on the back side, you have 100 feet of water on the upstream. That kind of looks at it, as we're coming across the top, just to show the picture. There's the Matrice 300 RTK with a P1. Up at the top, you can't see it, but that's a Skydio flying. And we used that for the internal bays because we're going to be going in GPS. And this is what it looks like. So I had a GoPro on my head and looking up, and it's just massive. So the flight over doesn't really do it justice. And you can notice how the depth, and you have these columns, and we need to map all of it inside and out. What's cool about, like on the Skydio side, is going out and, challenge here is the drone can't see water. If it sees water, it's going to go in it. It thinks it's open space. So we have to limit the floor, limit the ceiling, and then capture this. This particular data was at 1.3 millimeter resolution. And the LiDAR came in great because when you're doing a drone reality capture and you're letting ground control points, that's cool and all. But what happens whenever you have to make sure that you have a 110-foot wall and you need to get control points there? So we have to create wall control points, and we pull that out of the LiDAR data. So that was another kind of a trick that we ended up having to leverage to pull that together. So between the 2 projects where they achieved plan, capture, deliver, we wanted something repeatable, consistent, produce a comprehensive data set, develop composite maps to be able to use for inspection planning, and now we found some benefit on geological assessments and geotechnical as well. Future, hydraulic modeling, change and anomaly detection, GPR leakage. There's some things that we're incorporating now that's just continuing to build on it instead of staying static. So that's kind of where the future's going here as well. In a nutshell, project outcomes: improve safety, time and cost savings. Accuracy was impressive. I mean, we had the LiDAR data and said, okay, well, how does the drone photogrammetry and digital twin compares when you're measuring, and it measures and compares very well. Asset management, long-term digital twin that can evolve over time. So just one last comment here is, big takeaway is, you have to have good survey control. We found tremendous benefit of having the LiDAR to put wall control points that ensure that all of the data was really tied in. And yeah, and then having the artificial intelligence as well, where it can be a helper to show things. It just, what it found compared to what we would manually do was impressive as well. So the next one, I'm going to hand it over to my colleague, Cameron Schaefer, and he's going to talk about the next project.
Thank you, Carlos. So I'm going to talk about a lot of the same concepts, but give you a couple examples on the transportation side, just to kind of get a little different angle on the kind of data we can use and integrating AI in the projects that we're doing. First, with the Iowa DOT Integrated Corridor Management Project, this came out of our transportation planning group, and we really wanted to use Reality Mesh and see how far we could push it, see what we could do with it. And we kind of identified this as a pilot project to use and see what we could get the team, see how we could help inform what was needed for their specific purposes. So the first thing they needed was just a Reality Mesh for visualization. Easy, right? We'll take that, we'll give it to them, we'll let them generate fly-throughs. They took this and generated proposed models, put that over their design, win right off the bat. Then the team came back to us and said, hey, can we use this Reality Mesh to identify different classes of interest of particular assets? And we said, yeah, we think so. What are you guys looking for? So we sat down with roadway engineers. They came up with 11 different classes of interest that you'll see here that they were interested in finding over this 45 square miles of area that they're doing this corridor management study for. So we took the orthomosaic imagery that we had from the Reality Mesh, popped it into Neurala Brain Builder, which is a tool that's just going to allow for fast labeling and training of your data set through a web portal. We had 8,500 raw images to start with, and we trained 200. And so what you'll see here, it's those 11 different asset classes, the roadway medians, barriers, crash barriers, signs, drainage inlets, and so on. Trained 200 of those photos, and then dropped all 8,500 individual images into the code repository that was resultant from this task. What that left us with was being able to overnight process all 8,500 images and understand with an actual confidence interval how many of those different assets there are within that 45 square miles. So it gave us a count, it gave us an understanding. This is something that if we were to give to an intern, you're talking weeks to go through there and pan and drag and find all that. We were able to do this overnight with only training the 200 images. Team was impressed with that. We said that's a great use case, and they said, can you take it even further? Is there something you can do to actually generate a conceptual surface for us? And we said, yeah, we think so. So we took the resultant XY information that we got from the images, and we overlaid those on the RGB point cloud data that we had for those 11 different asset classes. From there, we got those different assets like the lane striping here, like the continuous yellow striping here, and then use that information across all those different 11 asset classes for that 45 square miles to ultimately deliver a conceptual level topographic surface that the team was able to use for their preliminary planning. So it's just an interesting case study on the highway side, what we're able to do with artificial intelligence and computer vision from the photo side. At the end of the day, when we kind of compared and looked at what a conventional workflow might have looked like with this amount of data, for that 45 square miles of point cloud, we're looking at 850 gigabytes. That's something that our team doesn't know how to use. No individual one person has a computer that's going to be able to leverage all that. When we were able to filter it down by asset classes, and then after those being converted to PODs for microstation use, we're looking at just about 425 megabytes per asset class. So this really helped the team to actually make sense of this really large data set, to find the information they need, and to get it in the right format to help integrate within their native design platform. I'm going to talk about one more project, same kind of concept here, asset identification through artificial intelligence. But this one's unique, and this I kind of classify as a beta at this point, but I think it's fun to share with this group of individuals here. So this is our Ontario Line subway program in Toronto, Canada. This is the largest project that HDR has had to date. It's 16 kilometers of a brand new subway line, $11 billion worth of construction value. From a reality capture standpoint, when we look at the amount of data that we're dealing with to date, and we're about halfway through, we've captured just about 15 billion points above ground and below ground for this project. We've got just about a 20 square kilometer, this Canadian project, reality mesh for the entire site. And we are integrating our LiDAR and our reality mesh as much as we can within the Civil 3D, Revit, InfraWorks, and Navisworks platforms, being that this is an Autodesk designed project that we have. We're bringing that same information into Esri, into 3D Scene. So we want to make sure we can distribute and allow our team, our client, even the public in some cases, to be able to visualize this data. And then what I want to quickly kind of feature here is a new tool we've been working on, which is the automated LiDAR data classification and feature extraction tool. I'm not going to go over all these individual steps, but Carlos kind of talked about the process on Diablo Dam. Very similar process here. The only difference is that we're actually running the AI on the point clouds themselves. It's not on actual photos. So we're starting with that registered LiDAR data. We're creating a training data set. We're selecting features that we want to classify on, and then we're improving, right? We're iterating. And at the end of the day, we've got it to a point where the training data set's created. We're using supervised ensemble learning, and we have automated detection of vegetation, power line, rail, manhole drainage, and just about 5 other asset classes. So I'll show it in a second here, but this is a tool we're looking to continually develop as you get more data. Your training data sets get better. You're able to identify more asset classes and improve on what you're able to deliver. So here's a couple examples of the type of training data set that went into this, right? So you're looking at light poles, transmission towers, and so on. And at the end of the day, we're taking that raw LiDAR data, running it through our ensemble learning code, and then what you get is that resultant classified LiDAR data that you see on the right. So just to show from a more kind of visual perspective what you're looking at from the raw, in this case, uncolorized data, you're looking at what we're able to get preliminary for here, just vegetation, rail, and power line. And similar to what we're doing with the Iowa project, this is really helping to work with our design teams and get them just the information they need in a smaller file format. And then we're also using this for different asset management use cases for an understanding across that entire 16 kilometers of mobile, terrestrial, and aerial LiDAR that we have. What are we looking at in terms of assets, and how are those going to change over time because of all the new construction that's happening with this project? So with that, want to keep it quick as Carlos promised, and wrap it up here with kind of the end results of this LiDAR data classification. Utilization for identification and tracking of our assets. That's kind of what we're primarily targeted for with this tool right now, through the automation of segmentation by our defined asset classes. And at the end of the day, we're just looking to continue to build the group of users that work with this type of technology, right? Get them more familiar, get them more excited, and make this more part of the day-to-day work that we all do. So wider adoption of point cloud data for our targeted disciplines and teams we're working with. So with that, if there's any questions, happy to answer.